Hi, I'm making this quick video as an introduction to the Camera Perspective Endpoint add-on for Blender. Perspective Endpoint, or PnP for short, is the problem of estimating the pose of a camera from a set of 3D points in world coordinates and their corresponding 2D projections in picture coordinates. This add-on is using a Python library for computer vision called OpenCV, which is not shipped with Blender by default, so you will need to either install it manually or use the option in the add-on preference panel for that. You can install the add-on in the usual way from Preferences, Add-ons, Install, and select the zip file. Once installed and enabled, the preference panel will inform you on the status of OpenCV package. The add-on adds a new panel in the toolbar of the clip editor area under the Solve tab, called Solve PnP. To illustrate how it works, let me load an example picture as a new clip. Let's say I want to find the camera pose relative to this Rubik's cube. And let's say I know the dimensions of the cube, and I already scaled my default cube here to match the real-world dimensions. I need to create a set of 3D to 2D point pairs between the 3D world space and the 2D picture space. To create the 2D points, I will add tracking markers to the clip. To add new markers, I can just hold Ctrl and left-click. I need a minimum of 4 points to solve for a camera pose. Then I have to add markers in the 3D space corresponding to the same 2D markers I just placed. I can use any object for that, for example, an empty object. Here I am duplicating them with Ctrl D and snapping them to the right corners. These points need to be placed in isolation in a collection. Then I can go to the Addon panel and point to this collection. If there is a camera in the scene, I can make it active. I can change the view to the camera view. Then I can click Solve Camera Pose. So what happened here is that the algorithm tried to estimate the position and rotation of the camera so that the projected image of the cube matches the picture. And it moved the camera accordingly. And it also added the picture as the background image. Now, as you can see, the projected image of the 3D cube is still not matching very well the actual picture. This is because the camera intrinsics are wrong. The perspective endpoint algorithm only solved the camera extrinsics. This is the camera position and rotation in space, but not the camera intrinsics, like the focal length and other camera characteristics like lens distortion parameters. This means that the camera pose calculation should only be done with a calibrated camera. The add-on also provides the option to attempt to calibrate the camera intrinsics. However, to use this feature, we need at least 6 points. The more points, the better, especially if you're trying to calibrate more than one single camera setting at once. You can find the current camera intrinsics under the lens parameters of the clip camera. In this case, the image mismatch is mostly because the focal length is off. So I will add a couple more points and try to fit the focal length. It is important to mention that the pairing of the 2D with the 3D points is done in alphabetical order. So you need to make sure that they are sorted in the same way, for example, in the dope sheet and in the outline. What I am doing is just place the 3D points in the same order I placed the 2D markers, so I should be fine. Now, since I only want to calculate the focal length, I will leave this checkbox ticked and the rest unticked. As you can see, the current focal length is 24 millimeters. I can click Calibrate Camera, And you can see now it changed to about 65 millimeters. Finally, I can solve again the camera pose, which will use the updated intrinsics. And as you can see now, the projected image matches much better the original picture. Now, this kind of problem, in this particular example, can be solved with other perspective matching tools like F-Spy. F-Spy is a great tool. I think most Blender users are familiar with it, but it has some different requirements in the sense that it needs some cuboid-like objects with parallel straight lines which are aligned with the Cartesian axis, X, Y, and Z. The beauty of the PnP method is that it's compatible with virtually any generic geometry, as long as it has a few points with known coordinates. I will quickly illustrate this with another example. Let's say I want to replicate this picture of an alarm clock as a render, and I want to match the camera position. In this case, let's say I know the focal length and it's 80 millimeters. This clock, as you can see, doesn't have many straight lines and right angles, but I still know something about its geometry. For example, I know the clock face is round, and the hour ticks are equally spaced, and there are 12 of them. So I will place a few marks based on this. I could use a mesh circle with 12 vertices to help me place the markers, or I can do it directly with numeric inputs. I move the first empty to the correct radius, then I set the rotation center to the 3D cursor, then Shift D to duplicate, R to rotate, Y to constrain to the Y-axis, then 30, or in this case 60 degrees, because I can put the marker every 2 hours, 6 points will be enough in this case. Then I can just press Shift R to repeat the last operation 4 more times. And then I will do the same thing for the 2D picture. If I go back to the camera view and I press Solve Camera Pose, the camera moves to the right place and puts the new image as a background. I will end with some words of advice on camera calibration. First, a disclaimer: be aware of the limitations of this tool. Generally speaking, full camera calibration for all the intrinsics for a given camera and lens is done by taking several pictures of a known pattern, like a grid-like pattern with many points, and taking an average of the results for each picture. This is not what this add-on is intended for, so I don't recommend attempting to calibrate too many parameters at once with only one picture. It will most likely give you wrong results. Every extra free parameter is an extra unknown, which makes the system of equations more difficult to solve. The more parameters you need to calibrate, the more point pairs you will need to find a solution, and also the more sensitive the results are to small positional errors in the placement of the markers. Specifically for radial distortion coefficients, it is best to place a significant amount of points in areas that project to places away from the image center, so closer to the edges of the picture. These are the areas affected the most by the radial distortion. Specifically for the focal length calibration, it is important that you place points at different distances from the camera. This is because if all points are at a similar distance to the camera, the solution is not well constrained, because there are an infinite amount of focal length and camera position combinations that will project the image in the same way. Look at the circles in this example. The camera is moving back and forth and changing its focal length at the same time, but the circles are projected in the same locations. On the contrary, if you choose markers placed at different distances to the camera, like for the square markers in this example, there is only one combination of focal length and camera position that will project the points in a given way. That's it for this introduction video. Let me know if you find the tool useful in the comments below, and if you have any improvement ideas or requests. Any feedback is very welcome.